All right, an educative a day keeps unemployment away. Just so that I have 5 videos for this week, which is my goal. My goal is to have 5 videos every week. I'm recording today on Saturday because I didn't record yesterday. Well, I recorded very early yesterday, but that counted for Thursday. So let's get the ball rolling. Turn off mine so I can focus for a bit. Hopefully, it shouldn't take too long. Sliding window. I feel like I'm more familiar with this pattern because I've done it before. It used to be the first pattern. So there was a version of this course that they had, but they revamped it and reordered things. Before, the sliding window was the first edition, and then it had the problems were broken down into easy, medium, and hard. They don't do that anymore, but I do notice that it gets harder as you go down the problem still. So yeah, let us get to it. Some stuff to read here, and then we do the first problem and hopefully the second problem if we have enough time. Let's go over the sliding window pattern, real world applications. Some problems we could solve with it. So it's used to process sequential data by maintaining a moving subset of elements called a window. The pattern is aimed at reducing the use of nested loops in an algorithm. It may be viewed as a variation of the two-pointer pattern, with the pointers being used to set the window bounds. Okay, that's interesting. Noteworthy. A window is a sublist formed over a part of an iterable data structure. I think the key note is that it has to be contiguous. It's used to slide over the data in chunks corresponding to the window size. The sliding window pattern allows us to process data in segments instead of the entire list. The segment of window size can be set according to the problem's requirements. For example, 3 consecutive integers with the largest sum in the array. We can set the window size to 3. So allows us to process the data 3 elements at a time. Why is it efficient? It isn't if for each window we iterate over all elements of the window, because that gives us the same OFKN time complexity. Instead, what if we focus on the element entering the window and one leaving it? For example, after calculating the sum of the first 3 elements, we move the window one step forward, subtract the element that is no longer in the window from the sum, add the new element that is entered into it. Next, we check if the new sum is greater than the first. If it is, we update the max sum so far. Now, each time we move the window forward, we perform at most 4 operations. Now, each time we move the window forward, we perform at most 4 operations, reducing the time complexity to 4n, that is n. The following illustration shows how the window moves along in the array. So window size of 3 elements, and you just move like that. You kick off. Next we're going to kick off 3 and add 0. Next we kick off 7, add 6, kick off 2, add 9, and so on and so forth. Repeated DNA sequences. Ooh, fancy computational biology. Hahaha. Sequence 1, sequence 2, sequence 1, sequence 3. Repeated sequences are AGA. Does my problem match this pattern? Yes, if these conditions are fulfilled. Maximum sum, subarray sum. It requires a repeated computation in a contiguous set of the data elements. A subarray, which such that the window moves across the input from one end to another. The size of the window may be fixed or variable, depending on the requirements of the problem. The repeated computations may be direct part of the final solution. The repeated computations may be a direct part of the final solution, or they may be intermediate steps building up towards the final solution. The computation is performed. Every time it moves, take O of 1 time, or a slow growing function such as a log of a small variable, say k, where k is less than or equal to n. If the editor does not support random access, you do not have to process the entire segmentation. Many. Well, I like this part, real world problems. I'm so glad they include this section because, bruh, without that, everything is kind of sus. It doesn't feel useful, you know. So telecoms, find the maximum number of users connected to a cellular network base station in every k millisecond sliding window. Oh, interesting. E-commerce, given the data set of product IDs and the order they are viewed by the user. Now this products are likely to be similar. Find how many times the products occur together in the data set. Okay? I have product IDs in the order that they are viewed by the user. Now these are products that are likely to be similar. Find how many times these products occur in the data set. Oh, interesting. Video streaming. There's a number of buffering events in a given session. Calculate the median number of buffering events in each 1 minute interval. Social media content mining, given the list of topics that 2 users have posted about, find the shortest sequence of posts by 1 user that includes all the topics that the other user has posted about. Two users have posted about, find the shortest distance sequence of posts. That 1 user has posted about. Matching problems that can be solved using the standard window pattern. So that problem left. Okay. 6 largest elements in an array. The 6th largest element in an array. Isn't this just a sorting operation? And then just pick item number 5. Just sort the array and pick number 6. That's what I would do. I'm gonna say some other pattern. You an array, find the longest substring, hey, keyword that includes 5 distinct characters. I'll pick you. 3 contiguous integers in an array. The highest sum. Find safe place for 5 queens on a what? I'm gonna say some other pattern. Yes, I'm sure I want to submit. Wow, I got it. I got it all. How about that? The sliding window is primarily used for solving problems that are contiguous subarrays or sequences within a large array. However, the 6th element requires examining the entire array and comparing multiple elements, which does not align. Yep. By using a sliding window through a string, you can maintain a continuous substring and efficiently track distinct characters within it. As the window expands and contracts, we can update the maximum length of the substring that satisfies the condition of having exactly 5 distinct characters. Find 3 contiguous integers in an array. This highest sum. So the integers within the array, I can track of the maximum sum encountered. Contiguous arrangements. Alright, problem solving time. Yay, my streak is alive. So we stand in the gap. We open the heart to receive what you have for us. There are come other ones in the string. All the contiguous subsequences of length k are occur more than once in a string. The order of the return subsequences does not matter. If no repeated substring is found, the function should return an empty set. Okay. All the contiguous subsequences come more than once in a string. The order of the return subsequences doesn't matter. If no repeated string is found, should return an empty set. New code types are reagents. For example, has a degree of again easy to for repeated sequences in it. AGT. AGT again. AGT again. TCA. Sequence 1. Let's do. Okay. All. I'll come more than once in a string. All of them. I'll come more than once. Look at them giving us a taste of computational biology. The only one that occurs more than once is that. TCA and TCA. The order of the return subsequences doesn't matter. So I can return this first, I can return this second. Empty set. Five. Wow, this is interesting. Oh, I have to just eliminate these options. AGCTG. AGCTG once. AGCT. AGCT. No G. AGCTG. Another one. Yep, this one. TTA. GC. TT. AGC. Occurs once. It doesn't occur again. Double A GCT. Double A GCT. Only one single A. Doesn't occur. Triple A GC occurs here, but it doesn't occur anywhere else. So, boom. Okay. CCA. Any other CCA here? CCA. GA. Only occurs once. AGA, AGA, AGA here. GC, GC here. GC here. More than once. Yay. AGA, GCT. AGA, GCT here. AGA, GCT here. TCC. It only occurs once. So, gasp. This is wrong. Oh no. AGAGC, AGAGC occurs once. Then AGAGC occurs more than once. What? Oh wait, are they saying? Huh. Because this is a subset of this. Oh, you're saying if it's full. If it goes complete, you don't return sub of that. Okay, makes sense. AGAGCT, AGAGCT. So you cannot now pick that again because they have to be independent. Yeah. Okay, fairs. That was useful. Okay. Usually there was a copy button. Let me create a legacy folder. And store all this inside. This is called repeated DNA sequences. Repeated DNA All right. I'll follow this thing. What's my input? Is a string, I assume, and the k is a number. Input, yes, should be string. And this should be a number. Okay. What does Copilot have to say about this? I wonder. Does Copilot have anything to say? Oh wow, that was quick. Wow. what does this do? So the result is an array of strings, a string array. This is a hash. It takes a string a number of times. Window start is 0. Window end 0 for the window less than. Okay. Window end plus plus. If the window end is greater than k minus 1. I highly doubt this would work. But the short way of finding out if it works is you know what? No, I need to leave here actually. Oof, I forgot to say O1. Because why not? I doubt it's gonna work. This is Copilot's first take. Does it have a clue? Nope. It's Copilot. Jeez. We're gonna keep our jobs, guys. We are gonna keep our jobs. It's nothing to be scared of. It's nothing to be scared of, for real. Yeah, sure. They want me to use a set. Not too familiar with using a set, although it did give me some clues. There's a window start, like a 2-pointer thing. Window start, and then key. There's the hash map, which can be a set actually. What does a set do? Kind of curious. I'll set in the room, man. Why you do this to me? Evaluate my curly ones. Okay, I get what that is, but I don't really know if I want to use it. I think I'd rather use a hash map. use that as a reference. I know I need window start, I need window end. Is it equal to 0? No, actually, it's not. It's equal to window start plus k minus 1, because I need the first window. Okay, then I can use this to store the strings that I find. So while the window length is less than that, the left character, is it the left character that I want? I don't think it's the left character. I don't want the left character. What I want is the substring. I want this. Store it in there. Perfect. Because how many? All the repeated substrings, right? That occur more than once in the string. Probably. Honestly, this is probably it. This might be the inefficient part, because it's probably looping through everything again to pull this out. So what I can do is this function might be inefficient. Or it might not be, actually. In my mind, this should work. Also, this frequency, if it's equal to 2, honestly, I feel like this should work. Might be naive though. It's like at times I feel like I'm using fuzzy logic to. Nope, it didn't work. Oh, something broke. TypeScript. Convert this. Stop being TypeScript, please. Oh, the type error. Results not defined. Did I not? It is. How is result not defined? Oh, I didn't copy that part. Hahaha. Lost. Wow, it worked. What on earth? Yeah. Hmm. I'd like to compare their solution with mine. I don't think I really need to step through the code, but I guess it might be useful to see what happened. For instance, this input. Let's just run through it real quick. And then it's supposed to give this. So then I just need one if statement here. When it's pushing it, and that's all really. Usually like putting them at the beginning of branches. Okay, so I have a substring. Let me watch a few things. This is the string. So start of the window is 0. End of the window is 7. K is 8. The first substring. Let me keep frequency. So we can watch, see what's going on. That was not equal to 2. It only occurs once. So move the window forward by 1. Move the end forward by 1. Get the substring. New substring. Store it in the hash. Still only once. It's less than the length. That's actually I can just see. Stop length. It's 21. We're at 9. We still have quite a ways to go. The next substring. Everything's 1. Let me expand this so I can see it. Next substring is this. 1. We're almost there. We're at 14. Everything seems to be 1. It hasn't changed. One. This at the top. Ah, 1 is 2. Nice. So the result will have something for once. Another one is 2. Yay. That took a while. But we see it. So that's nice. Let's see it now. Let's review their own solution. And get rid of this gobbledygook here. It made no sense. from Copilot. Let's look at their naive approach. Iterate it and add all the unique substrings to a set. I think that's what I did. Oh, it has a name. Raven carp. A rolling hash. Well, realistically, if I was seeing this program pop up for the first time, there was no way I was going to come up with no, I'm not interested. I think I know this course. Why is it not showing the link? Because it's not a link. What's this? Not really interested in that. Current window. It's already present in the set. If it is, it's repeated. Otherwise, it's not being repeated. So yeah, that could be the hash to the set. Whoa. Okay. Okay. Wow. We're using ASI. Thank God I didn't waste my time trying to figure that out. Because this looks like the product of a PhD. I'ma just say. Yeah, we add this hash value to the set and slide window one character forward. Computing hashes. I'm hashing the number. That's encoding it, basically. It's a form of encoding. Now, if you're interviewing and you expect someone to come up with this on the fly, or to not have this memorized, then shame on you. Or to have this memorized, shame on you. The sequence has been repeated. There is identity happened, and is therefore identity happened. Take near time. In the worst case. This is very weird time complexity, yo. Why not just call it linear? We need a hashing function and cause that time hashing. Polynomial ruling hashing technique. Okay. Okay, is a substring. We only need 4 plus we need 4 times our alpha before. Why is this so hard? Like, what's all this? I mean, it's not hard, it's basic arithmetic, but like, why is so much basic arithmetic for such a straightforward solution? Oh, but then if I want to optimize, well, at least I know there's something fancy going on in this problem. I don't need to know all these details. I just want to see code, man. Show me the code. Okay. Wow. So it literally requires an encoding step. Blow my mind. Blow my mind. So there's an encoding step, and if you have to know that AC, GT are like standards. Okay. This is horrendously complex. Like, for problems like these, I just take note of them, because I ain't got the strength, to do this. Except I'm in a situation where I'm going to save like $1 billion. I'm definitely going to go with this solution, like in practice. Like, just straight up, like, leave this stuff alone, star. Leave this stuff alone. Right, man, that's crazy. Yikes. Okay, all that. No, man. Please. Have mercy. Have mercy. Have mercy. What is power? Raised to the power looking for here? What is it looking for here? What is it looking for here? This is super complex. Yeah. All that to get woven. Woven. Yeah, this is a trash question. This is FYI. Yeah. Good to know. I mean, good to know, but definitely not something I would have come up with I mean, now I know it. I can memorize it, I guess, if I need it in it like an algorithm. But yeah, the other way, this just works. All right, this just works. So all of that other stuff, I don't know, man. Yeah, a rolling hash. Traverse its compute the hash, check if it's present in the set, repeat it for all substrings by sliding one character forward in each iteration. After all substrings will be evacuated, return the output. Oh, the choice of the hash function can affect its time complexity. There's linear time, then there's constant time. Since we only have 4 possible, we assign the numerical values to the nucleotide. Use the value for alpha, since it shows that each nucleotide is assigned a unique value in a nominal hash function. For hash ATG, I get 1 times this, 4, because T is 4, times this. And it's like a base 4 thing, right? Because it's like number bases to the second power of the first power. Like if it was base 10, it's 10 times 1, that's a unit, then the tens, and there's the hundreds. Yeah, this is nasty. some nasty piece of work. I've not come across this in my day-to-day job, doing quite simple, quite complex things, really. But just not this stuff, not having to hash stuff myself, except passwords with bcrypt. I'm trying to avoid having to do that as well. Don't tell me. So you can hash with linear time, you can hash with constant time. And I'm assuming we didn't go with the linear time. Because with the linear time, we're in danger of having the same time complexity with the naive approach. And you're hashing with the ASCII code. So every character corresponds to a code. A has a number in ASCII. Same with C. A and C is A is 65. C is 67. B is probably 66. As I C removed from the hash, so you subtract and add. It simulates taking it out and putting something new. But the issue is CT and TC will be the same. You need to compare. Let's see if they're identical. In this case, they're not, so yeah, this. So there are no characters set forward. The sequence in the window to compute the hash of CT. And there's add to remove from the previous hash. And then add it again. So you compare the sequences. So they're identical. The sequence will be different to the output. Using the hash and then compare the string of the hash and you go take linear time in the worst case. Think about the cars on each side, which will make them in the time, so the naive approach. And constant time, polynomial rolling hash technique. Is it constant? Like the base, number base. Constant horizontal sequence, because it's of string length. Constant nucleotides. Here's number 4, constant translation nucleotides and running from the hash function. This reduces the number of collisions. Randomness is not necessary to the constant nucleotide form effect. Any number greater than the number of nucleotides. The idea is to choose a value that's large enough to avoid hash collisions and stable relative to this response of measures of arithmetic overflow. So let's see. Hash value is 6. The contribution from A. And then add a contribution to T. Same hash value. This can't be right. TC. So I started with AC is 6. CT. CT is 2. AC is 6. Exactly. Crashed probably by the base. This is crazy town. Wow. This is super complex. Well, enough. That's one problem for a day. It took way too long. That is not trivial. Not trivial at all. But we've come to the end of today's session. Trade-offs, right? Trade-offs. Yeah. Robin Karp algorithm. It's like a rolling hash. The hashing is not too bad, right? It's not too bad of a thing to have in mind. And it does make sense. Linear time behavior and all that stuff, but this works too. Naively. You'll find many code bases are filled with naive solutions out in the wild. Maybe not at Google, right? Where like optimizing this could be worth millions of dollars a year in like energy costs. But for most cases, for most everyone else, that is not the case. That is not the case. I think I'll leave this for next week, Monday. These next ones. This was a very sobering introduction to the sliding window pattern. I feel like this would have been a better introduction, but it is what it is. To each their own, yeah? To each their own. Yeah.